Hi everyone, please, as always, write hi to the channel or your favorite emoji. And as always, let's give everyone a minute and we will start. Okay, awesome. I see that you can see and hear me perfectly. So many people, wow. So let's start. Hi everyone. This is the second lecture of my Haskell course for beginners. Previously, we were learning about fundamentals of the functional programming and Haskell, and today we are going to talk about how we can use a flexible type system to write even more awesome stuff. And we are going to start with pattern matching, which is another very common and fundamental concept of functional programming. So we as human beings or as developers, we have an ability to recognize patterns, some common parts of different objects. And this is important for us because we can notice these common parts and we know how to deal with such things. We don't need to repeat our previous knowledge, like relearn anything from scratch, and it's important. And patterns can be small, like a simple value, like all even numbers in the list, or they can be big in programming, like architectural patterns, like how you write tests, how you log your messages, how you handle your exceptions. But we are not going to focus on such high-level patterns in like software design. Today, we are going to talk about small patterns. And when I say pattern in Haskell, I mean that pattern is a specific value or shape of an input. It describes some way how the input looks like. And let's look more at examples and start straight away. So the syntax for working with pattern matching can be of two forms. So first one is the following. You write the function, its name, and the type signature as previously, and you write its name, but you write the name so many times on so many lines, how many patterns you have. So if you want to handle different patterns, you write the name many lines. And when your function takes an input that satisfies this pattern, that matches this pattern, it will behave depending on what you put on the right-hand side of the equal sign. So that's why the name is pattern matching. We match our input to the pattern and we see which one actually matches. So previously you may wonder, like, why do you need to repeat the function name twice? Like you write its name, its type signatures and name again, and then its arguments and names. Can we just combine and like arguments and types together as it's already done in all other languages? But now I hope you can see why it's done this way. It's because functions can have multiple lines. They can match with multiple patterns. And this is the way how Haskell understands that these are the patterns for the same function. You just put the name of the function before. Alternatively, you can use the case of expression. So the syntax is similar to the patterns, but you don't repeat the name of the function multiple times. You just start as always, as previously, and you use the case keyword. You then apply it to some variable, to some value. And again, you specify all the patterns. Sorry, and the results depending on the pattern you get. So this is basically the two same ways. And depending on how you prefer, which style you like, you can use either of them. So sometimes your function name can be really long and you don't want to repeat it on each line multiple times. So you use case of, but on the other hand, it may look more neat in the case of, depending on situation. So let's look at some examples. The first example is function not. This is a standard function which takes a boolean and returns the other boolean. And we see how it works with pattern matching. If it takes true, it returns false. And if it takes false, it returns true. So the Boolean has only two values, true and false, and we can see that this function handles all our inputs, all possible values. But not all data types has so few values. So that's why right function is 0 using pattern matching. So it takes an integer number, and there are like lots of numbers. We cannot write a pattern for every number. It will take lots of lines of code, but we are not interested in all numbers. We are interested only in patterns that we capture. So function is 0 if it takes 0, a number 0, it returns true. Otherwise, if it takes some other number, some variable, it returns false. So you can think actually of variable names as of like special cases of patterns. So they on the other hand, so on one hand, they don't match anything, but on the other hand, they match all other data types. They don't bring any information about values, but they match all values. And here's an example how we can use the case of expression. So let's write a function that takes two numbers and it takes an operation for these two numbers, but in form of a character. So if the character is plus, we add two numbers. If the character is minus, we subtract all numbers and so on. But again, there are many characters, but we're interested only in 4. But people actually might pass any possible character to our function. There is no guarantee that only these 4 will be passed. So we need somehow to handle all other cases. And here we can use this so-called underscore pattern. So underscore is a pattern that matches everything. And in our case, we just return 0. And it's very important to keep the indentation straight, because remember, Haskell is a layout sensitive language, and it's very tempting here, like for like code prettiness reasons, to write this underscore under the math symbol, not on the left side, but it won't parse. You will get a parse error in Haskell, and just you need to align all the patterns with the same indentation, like 2 or 4 spaces, for example, depending which you prefer. These are just simple patterns, but we actually have a more complicated data structures like lists. Remember, we spent lots of time last time understanding lists, and we know how patterns work for values, but let's see how they work for lists. Well, actually, they work pretty the same. So there is simple pattern like empty list, which is a square brackets without anything. And we can write a function is empty that takes a list of numbers and returns true if the list is empty. And if it just takes an empty list, then true. Otherwise, we don't care what the list. We just use an underscore pattern and return false. So let's write a more interesting function. So we want to write such function that takes a list. And if the list has exactly 3 numbers, we want to find the sum of the first and the last numbers in this list. So again, we just put our 3 numbers between the square brackets. We don't care about the middle number. So we just use underscore. For the first and the last, we give variable names x and y, and we just add them. Otherwise, again, let's just return 0 because we don't care about other cases. And another function, let's now practice case of expression for list. We want to write a function that takes a list and returns true if the list is exactly 1 0 or exactly 2 zeros. So you see that the name of the function is kind of long, and I don't want to repeat it on every line. So I'm here using the case of expression. And again, I'm matching against the list. And at the same time, I'm matching against the values inside the list. So if it's 1 0 true, 2 zeros also true. So pretty straightforward, patterns can be nested. But let's look at a more interesting example. Now, I want to write such a function that returns true if list contains at least 2 elements. So 2 elements, 3 elements, 4 elements, 5, and so on. So my first attempt is to write like this, like put 2 underscores between the square brackets, because I don't care about the values itself. I just care about the size of the list. And does this function actually work? Does it return true if the list has at least 2 elements? The answer is no. This function returns true if the list has exactly 2 elements. So this pattern with square brackets is for lists of exactly this size. And there's nothing wrong with the function. It's just its name is wrong and documentation is wrong. We can just rename the function to something different, like is exactly 2. And lots of bugs can be fixed with just renaming function. It's not a bug, it's a feature. But still, we might want to write such a function that takes list and checks if it has at least 2 values. So how could we do this? We could use the function length, like to compare length with a number. But remember, length doesn't work with infinite lists. So if I call length on an infinite list, it won't work. And I also can't like write patterns for all lists of all possible sizes, like size of 2, 3, 4, and so on. Again, because there are infinite lists, and I don't have infinite lines of code and infinite time to write all these patterns. Is there a way to write it better? And actually, yes, there are structural patterns for list. And essentially, when we think about the list, what is list? List can be, actually, there are 2 possible lists. There are 2 ways how you can get any list. You can get like by either having an empty list. So a list can be empty, so list can be empty. Or you can get your list by prepending some element in the beginning of some other list. So these are actually 2 possible ways how you can create any list possible. And this colon operator, which we use to add elements at the beginning of the list, it actually can be used as a pattern, like a structural pattern. And the element on the left side of this pattern is called the head of the list. Usually the name is X. And the variable on the right side of this pattern is the tail of the list. It has a type list and all other elements without the first. It's called axis. The naming scheme, because it's like X and axis is like axis is like many axes, like in English, the plural form of anything. So no special meaning, but just common naming convention. And because usually names don't really matter much, don't contain lots of useful information. So yeah, this is like nice structural pattern. We can use it, but you say, wait a minute, you can say, previously we constructed lists with square brackets. We put elements between the commas. And now you're telling us that the only way to construct this is by prepending elements. How does it work? Well, actually it works because this syntax of list literals between square brackets is just a syntax sugar for prepending elements in the beginning of the list. And Haskell has tons of syntax sugar. And if you just write the 3 elements of just like in comma separated, you can think of this as appending 2 in the beginning of empty list, and then prepending 1 to the resulting list, and then finally prepending 3. This is how you can get, but it's more convenient to write it in square brackets. Basically the same. So now let's use, like we have this knowledge, let's use this knowledge to write some more interesting functions using these structural patterns on lists. So previously we wrote a function that a better version of a head. So head fails on empty list, and we patched it by implementing a new function that takes a default value and returns this value on a list. So we previously wrote this function using if then else expression and using standard functions such as null for checking if the list is empty and head for taking the first element of the list. But now we can write this function using pattern matching. So the first case, we have a variable def for default values, and we check on the list. If the list is empty, then we just return the default variable. Otherwise, we don't care about the name of the default value. So we just use underscore. We pattern match on the list, and we are not interested in the rest of the list. We are only interested in the first element. So we use underscore instead of the tail, and we just take X and return X. This is just the function that takes the first element of the list or default value if the list is empty. Let's write a function that drops the first element of the list. So again, the list can be 2 possible cases, like empty or not empty. If it's empty, well, there is nothing to drop, we just return an empty list. If it's not empty, we use this colon operator for pattern matching, and we don't care about the first element of the list. It's really convenient that it's on the left side, so we just drop it, we don't care, we use underscore pattern and return X's, the list without the first elements. Let's write more interesting function with nested patterns. So this is not actually a funny emoji. This is an actual Haskell pattern. And what it does, we want to write a function that takes a list and checks if the second element of the list is 0. So what are possible cases? The list might be empty or it might have less than 2 elements, or the second element might not be 0. But we want just to capture this ID in a single pattern. So we use this colon pattern, colon operator multiple times, because why not? The first element of the list on the left side of this pattern, and the rest of the list on the right hand side. But it's also a list. We can pattern match on it again. So here we just pattern matching on the list. We check if it's size at least 2, and we also using nested pattern matching to check if the second element of the list is 0, and we return true. Otherwise, all other cases we are not interested in that. They don't match, and we return false. So I guess now you know how to write a function that checks that list has at least 2 elements. You can use nested structural patterns. And these patterns, they really shine when you want to write recursive functions on list. So here's how you can write a sum function that finds sum of all elements in the list using recursion and pattern matching. So if we are given an empty list, we return 0. Otherwise, the list is not empty, and we add the first element of the list to the recursive call of the sum to the tail of the list. This is straightforward. It's not the most efficient implementation, like not because of Haskell or lists or laziness, but just the way it's written. It will need to unroll all the entire list. But still, it's pretty nice and it works. And it shows how you can use a pattern matching for writing recursive functions. Let's improve one of the functions that we previously wrote. So on the first lecture, we wrote a function that takes a list and an element, and it counts how many times this element appears in the list. So we wrote it something like this, using a nested if then else expression, using null functions and head and tail. And I mentioned that it's not the best way. And yes, actually there is a better way, because functions head and tails, they're unsafe, and ideally we should avoid them. And here's a better way to write this function using pattern matching. So as before, we use this recursive helper function called go. We still have a helper accumulator, and we pass 0 in the beginning to count how many times the element appears. But now we use pattern matching. Instead of checking the function with the list with function null, we see if the list is empty, we just return our accumulator, how many times we found the element so far. Otherwise, if list is not empty, we compare the first element of the list with our given number n, and if they are equal, great, we increase our accumulator by 1 and continue with the tail of the list. Otherwise, we just continue with the same accumulator and with the tail of the list without the first element. So you can see that this is like much shorter version, much cleaner, and it doesn't use unsafe functions. So actually, as I mentioned, you don't need to, and you actually shouldn't use functions head and tail anymore. And if you notice that in your function, you use functions like head and tail for the same list, there is 100% chance you can rewrite your function with pattern matching and avoid using unsafe function. So our count function is not unsafe, but still you kind of need to look at the code to make sure that it's safe. Like, did we check that list is empty before using the head function? Like, and if we refactor this function, will it still hold? But here, if we use pattern matching, there is no way this can hold. If the pattern already gives us the head and the tail of the list, there is no way this function can be unsafe, and it works. So pattern matching is great, and please practice pattern matching skills. So we looked at some examples of nice patterns, but let's see what can go wrong if you use patterns incorrectly. So again, let's write the function is empty, but a little bit differently. I switched the 2 lines of the pattern, and the first pattern is underscore. Like, I don't care about the list, but if it's empty, it's true. What's wrong? Well, actually, the order of patterns matters. Semantically, Haskell checks your input with patterns from top to bottom. So in practice, it has some great optimizations to not do this if the meaning is preserved. But in reality, like, the patterns are checked from top to bottom. And if your first pattern is underscore, well, it matches everything. So actually, if this function is empty, it will always return false on any list. So not really useful. Again, what's wrong with this function? It's head or def. It's very similar to what we wrote, but our first pattern is we gave the name to the list L. And again, this function will always return the default value because variable, it always matches. Again, order of patterns matters, and you can think of variable or underscore as this kind of like whole patterns that always match anything. So be careful when you use these patterns. We want to write another function that takes two numbers and checks whether the numbers are equal, whether they're the same. And we like writing by giving them the same name, the same variable name. But this doesn't work because patterns don't work like equality on the name variable. It works on like some structure and values, not on the variable names. Some programming languages support patterns by the name of the variables, and in some languages, something like this same function works, but not in Haskell. Another function, this is more or less how the head implements in base. So if the list is not empty, we just return the first element, and that's all. We don't cover the case with empty list. And yeah, this is a problem. We don't cover all cases. The lists can be empty. And if you give an empty list to head, the function will throw an exception. So in Haskell, it is possible not to cover all cases, but it's a shame. So please cover all cases. And the final function is greeting. It takes a string and returns Boolean if the string starts with a greeting. So like 3 characters, hi and exclamation mark. We pattern match on the list. We use nested patterns. We check characters. What's wrong with this function? Actually, nothing is wrong. It's correct. It just still looks ugly. There is no nice way to pattern match on the prefix of a string. Like it's really convenient sometimes, but you can do this with some maybe other functions on other language features. But for now, if you want to check if the string starts with a specific prefix, you need to pattern match on each individual character. So yeah, these are common pitfalls with patterns. And another very important concept of functional programming is totality. And we say that the function is total when it's defined for all inputs of its type. Or in other words, when you give any value of this type, you always get a result, always get output. If it's true for the function, we say that the function is total. And if function is not total, so it's not true, we call it a partial. This is very important. And it's a nice property of a function because when you give it any inputs, you don't need to care whether you pass correct inputs. So it doesn't matter what you pass to this function, it will always return you a sensible result. And if you use multiple such functions, the composition always also will be a total. It's pretty nice. But you may think that, okay, it's maybe really hard like to check how I can make sure that I really covered all the cases that my patterns cover. But this is a nice part. You don't need to do this manually. You can ask JHC to do this. It provides tools for telling you if you don't cover all the cases. So let's look at an example function. It doesn't matter what it does, what it matters, what patterns it has. It takes a Boolean and a list of elements. And if it takes a Boolean true and an empty list, it returns 0. And if it takes a Boolean false and a list of 2 elements, it returns the sum of these elements. I hope at this moment, it's pretty obvious that this function is partial, so it doesn't cover all cases. For example, what if you give true and not empty list to this function? Well, it will return. Well, it will fail. But how you can make sure general case? The nice part, JHC can tell you if you don't cover all cases, JHC will output a warning saying that this function is partial because it has non-exhaustive patterns. Patterns don't cover all possible inputs. And the neat part is that JHC will print all the remaining patterns, and we can see them. So the function takes the patterns that are not matched are true and not empty lists, colon operator. Okay, makes sense. It has false and the list at least 3 elements. So we cover 2 elements, but we haven't covered more than 3 elements. Okay, yeah, makes sense. A list of a single element. Yeah, and an empty list. So these are the 4 remaining patterns that are not covered by our function. Okay, you don't worry about patterns, but sometimes you may define like lots of patterns, and some patterns may overlap. So they might cover the same inputs. You don't need to worry about this as well. If you cover with your patterns my values, JHC will tell you that some patterns are redundant, they are not reachable, or they just overlap. And some of the errors from the previous slide, actually GHC will tell you. So this function is like has some redundant patterns. And this is a hint that something is wrong, but it's important to understand what is wrong. So we talk about patterns and patterns about on standard types, but the standard types are not always enough. Sometimes it's convenient to work with multiple types at the same time. So I want to have string and a number at the same time, like pair of these values, and I want to work with them together as if they were a single value. Is this possible? And the simple way for achieving this is for using tuples. So tuples is like lists, but elements of tuples can have different types. You can have pairs, triples, quadruples, and to create a tuple, you put elements between the round brackets, and again, you separate them with comma. And if you check the type of tuples, you will see that the type of character X and true is a char and bool types of all elements. And as I said, different elements of tuple can be different type. And you have some nice functions to work with tuples. So function fst returns the first element of the pair, and function snd returns the second element, as the name suggests. But these functions are defined only for pairs, so not for triples or tuples of bigger size. And because all tuples are different types in Haskell, so you cannot really write functions that work for any tuple, that they're different types, but you can write your own function to extract elements from triples or more. And here's how you can work with tuples. So let's say I want to split my list by the third element. So I take a list and I take its first three elements as the first element of a pair, and I drop 3 elements of the list and put the result as the second element of my pair. And you see that this function works. We can split it by the position 3. And if you want to consume tuples as your input, you can pattern match on them, again, using the round brackets and commas. And this function takes a tuple of Boolean, number, and a string. And if Boolean is true, we return the string with the number and we show the number. Otherwise, we just add string to our hard-coded string literal. And again, this function works. So you can, if you want to pass multiple arguments, you can pass them as a tuple. Usually don't need to do this because you already can specify multiple arguments, just separate them with arrow, and it's better for partial application. So with tuples, it's not that easy to apply functions partially. It's possible, but more work. But it's convenient to, if you need to return several values from a function, you can use tuples. However, tuples are kind of like primitive way. So I guess you have a tuple of string, list of booleans, char, boolean, another. It's kind of like just a bunch of types, it's unordered, it's like some chaos. Is there a better way? And one of the ways to have a more flexible types, to define your own types in Haskell, is algebraic data type concept. This is another fundamental concept of functional programming. And algebraic data type is just a type that can be created in 2 ways, either using a product type or a sum type. So that's why the name algebraic, there's 2 algebraic operation. And the product type is when you combine types and you have both, and the sum type is when you have choice. Let's look more at the example. What does it mean? So a product type is a combination of 0 or more types, and they combined, and you have values of all the types. So you can think of a type as like a set of possible values. So the type Boolean is a set of 2 values, true and false. As a set of numbers like int type, a set of all possible numbers. It's a machine word like 64 bits. So it's like a lot of numbers, like really a lot, but still finite number. And string is like, oh, well, strings, there are infinite strings. And if you have a product of these 3 types of string, int, and bool, you can have all values of any type, but the value of the product of these 3 types should contain a value of each type. So, we're already familiar with products. Actually, tuples are the simple form of product type. If we have a product of string, int, and bool, we have a triple, which contains a string, a number, and a Boolean. And the string can be any string, the number can be any number, and the Boolean also can be any of the Booleans, but we must have all of them. This is a product type. Just the combination of all values. And tuples kind of primitive, but in Haskell, we might want to have like our own custom data types. We might want to add additional information to our types, and you can create your own custom data types using the data keyword. So how it works, you use this keyword, you then write the name of your type. So we have a type user. Then after the equal sign, you put the constructor. This is the way how you are going to create values of your type, and how you tell Haskell that your type is different from the others. And then again, space separated, you just put all the fields, all the values that you have. And again, this is a product type. It's a product of 3 types: string, int, and bool. Or in other words, it has 3 fields: string, int, and bool. And this is just simple type. So what we can do with this type, I write a bit shorter. And I'm adding this special line deriving show. I'm going to explain deriving in the next lecture, but so far you can think this is a special line to make your type displayed in GHCI. So automatically convert values of your types to string. But if you don't write the deriving show, GHCI won't be able to print your values of your type. And when I show some data types, I will assume that this line is present, even though I won't always write it on slides, but it's important for GHCI. So back to our data type. We have this data type. What we can do with this? Well, we may want to extract these fields from data type. So we have 3 these fields. How we can extract them? How we can write getters that get fields? Well, this is just a simple function. The simple function, for example, get username. Assuming that the first string is a name, it's a function from a user to string. We use pattern matching. So this is what we learned before. Pattern matching, we use the name of the constructor. And we're interested in the first field. The first field has type string, and we are not interested in other fields. So we are just using underscore instead of them, and we extract the first field. If we want to extract age, the second field, we just put underscore on the other fields and we extract age. So it's pretty straightforward pattern matching, but we might also want to be able to change our values, like to write setters that change some of the fields. But wait a minute, values in Haskell are actually immutable. You cannot change values of Haskell. So what you can do? Well, you cannot change existing values, but you can create new values from the existing. And here's how a setter could work. For example, we might want to change a name of the user. So we take the new name, we take user, and we return new user. The new user will have the fields, all other fields the same as the previous user, but it has the name that we are given. This is our user. And you can see that we actually used constructor here to create a user. And it makes sense because constructors in Haskell actually just plain functions. They just start with a capital letter and they create your data types that you defined. But if you check the type of your constructor, it's a function that takes a string, an integer, a boolean, and returns your user. So remember, in functional programming, everything is a function, and this is neat. And we can extract the name to check our getters of a user, and we can set a username to check to see that we actually created a new user. So this is how you can work with data types. But if you're coming with some experience programming background, you say that it's really inconvenient, like to write getters, to have this bunch of fields and to write such setters, like really lots of boilerplate, and it's really easy to introduce errors. If you have 10 fields and all of them are strings, well, good luck getting this right. Fortunately, Haskell make life a little bit easier for you with a feature called records. And the records allow you to write data type in a slightly nicer way. So again, the same name, the same constructor name, but now we have names of our fields between the curly braces and separated by comma. And we write the type of the field on the right side of the field name after the double colon. So this is how you define type. And if you define your data type, your product type, so this is still a product type of 3 types. But if you define this way, you get several nice features. First of all, you get all these getters generated for you. You don't need to write getters. So these fields, as we wrote them, this will be a top level functions with the corresponding types. So username takes user returns a string, user age takes a user and returns an int. And You may wonder why I added the prefix user to each field. And this is because these fields will be top-level functions. But in Haskell, it's forbidden to have functions with the same name, but different types. So for example, if I have a user and it has age, and if I have an animal and animal also have age, and then I define them both as records, I will have two functions, one from user to integer age and another from animal to integer to age. But it's not possible. Haskell doesn't allow to have such functions. So one of the simplest way to do this is to disambiguate your fields by adding the data type prefix. It's not the only way. And in Haskell, it was painful to deal with this problem for a very long time. There are multiple ways in the ecosystem with different levels of complexity. The latest version of Haskell compiler JHC has a new feature that promises to solve this problem once and for all in a nice way. But in our course, we are going to use the classic way, the classic Haskell syntax. So you get these getters. You also get, if you define your data type as a record, you get initialization using names. So you don't need to put arguments in space separated. You can use names. And you also have a record update syntax, which allows you to create new values. And let's look at some examples. So let's create a user using this initialization record syntax. And we just put our values between curly braces. And we just write the name of the field and its value. And you don't need to have the same order during initialization that you have in the field. So it's order independent, which is nice. Again, if we wrote this deriving show line, we can print our value and it will now print also as a record. So, and if you want to create a new value of user, we can just take an existing value and put new values between the curly braces, new fields, new values of the some existing fields. And the fields that we haven't specified, they will have the same values. But what we specified, they will change. This is really neat. If you have lots of fields and you want to change only some of them, you can just specify only part and you will get the rest. So just like copy of the existing value without all fields changed. This is nice if you have lots of fields. And usually people use records for product types in Haskell and not just plain data types. Okay, this was the product type. Let's look at the sum type. So sum type represents choice. If we have a sum of string and int or bool, we have a type that contains either any string or any number or any Boolean value, but not at the same type, at the same time. You can't have them as a string and number at the same time. This is for products. So sums represent the choice. And it's a bit more difficult to understand, again, if you're coming from another language, because it's not really popular construction. But if you think from a life perspective, it makes sense because you can either have like both stuff, both things. You can have an apple and a grapefruit, like both things, or you can have a choice. For example, you can eat a burger or play video games or go for a run. So you cannot do these things at the same time. Well, maybe if you try hard, you can, but it's actually a choice that you can do. And a lot of things in life represents this choice. And in Haskell, you can capture this with a data type and how it looks like. So the simple case of sum type is enumeration or enum types. So let's write a simple enum for color. We have three constructors. This data type has three constructors. The first constructor is written after the equal sign, and then we use vertical lines for other constructors. So these constructors don't store anything inside, so no strings, no numbers, and there are only three values of the color types. These different constructors, they are also sometimes called constructor tags. And actually, the already familiar data type bool is defined exactly as a sum type. It's in simple enumeration, so it's not a built-in value. It's just defined as a simple data type. And when you write such data type, you can use pattern matching on this. For example, we want to convert our color to a string, and we just, for example, use the case of expression, and we match on all the constructors, and we tell what the string to return on each constructor. And if you forget to write any of the constructors, again, JHC will tell you that not all the cases are covered. You forget these constructors. And what's more important, and which is really great, if you, after some time, you decide to change your type, you decide to add more constructors, JHC will now warn you that, okay, these functions, they now don't cover all the cases. So you don't need to worry about forgetting to update some functions if they match on all constructors. And because of this feature, it's encouraged often to match on all constructors, even if you want to specify behavior only for a few of them, because if you use this just underscore pattern, JHC won't be able to tell you about forgetting constructors. Otherwise it's neat. And again, you can use this function. Since it's just any data type as any other data type, you can have it inside list, and you can apply a function to every element of the list using map, and you will get a list of strings. So really neat. So enumerations are a simple form of some types, but there is more more involved, more flexible. Let's look at this data type, which is result. It's a sum of two types. So it has either a string or an integer. And this is like a result of some computation or evaluation. So the result can be an error with some message. So this is a string for message telling us what went wrong. Or it can be an OK constructor, which is an actual value. And how we can use it, this data type? We can use it to write a safer version of a div function. So, we cannot divide by 0, it's an exception. But if we, instead of returning a number, return result, we can pattern match on the number. And if it's 0, if the second number is 0, we return error and a string like division by 0. Otherwise, we just turn OK and a division of two numbers. Well, what we can do with this data type, we can actually now pattern match on it and again convert to string to show eventually. So if we take an error with some message string, we just add this message to the error string. And if we have a result, we just show result. It works. And you can see that it works as promised. So it's like we have, you see, it's like two constructors. So result has two constructors. You don't have string and the number at the same type. It's a choice. You either have an error message or you have a result. And how you tell the difference between them is like a string or result. You use the constructor names. So constructors, these tags, they tell you the difference, what they tell you. You can pattern match on the constructor and you can extract the relevant part. And some types can be of different shapes. So for example, data type for answer, it either have no result, just constructor no result without any fields, or result with some number. Or you can have a data type with some property, maybe some property of a form or an element. And the first constructor has a number, the second constructor has a boolean in the number, and the third constructor has a string. So it's really flexible. And because of the way how you define data types in Haskell, the Haskell type system is usually called the sum of products. So you have multiple constructors on the same level, separated by vertical, and each constructor might have 0 or more fields. Like this is constructor kind of like product type. So that's why the name is sum of products. Okay, so let's return back to our example with lists. And let's think how we can write a data type for a list. Is it really built-in data type, or can we define it on our own? And if you think about the list can be either empty list or an element added to the list. This actually looks like a sum type. So we have two constructors, two choices, and yeah, we can define it as a Haskell data type. So empty list, we can just have a constructor called empty without any values. Otherwise, it's some element added to the list. We name the constructor cons. It's a standard name for constructors that add elements in the beginning of the list. So we have a number. So this is data type not for general lists, sorry. It's data type for just list of numbers. And the second element of our cons constructor is the list itself. So see, we're referring to our int list recursively. And we have recursive data type, so there is nothing wrong. This const stores number and another list. We can write functions for our own data type. So let's write a function length that calculates the length of the list. The length of an empty list is 0, so no elements. The length of some element prepended to the list is 1, so we have at least one element, and we add this one to the length of the tail, to the results in the list. So pretty straightforward. And we can write a function that construct such recursive data types. For example, function n0 and zeros, it takes a number and creates a list containing n zeros, how many are specified. So if you want to have zeros, we just have an empty list. Otherwise, we add 0 to the list of size decreased by 1. And again, we can check that these functions all work and allow us to create a list. So cool, it actually can have recursive data types, like nested data types, and this power allows you to create really flexible features. These are the ways how you can create your custom data types, but you don't always want to create new types. You don't always want to have custom data types. Sometimes you just want to have a different name for a data type. And Haskell has a feature called type. It's a keyword, which allows you to define like a new name of an existing type. And in any place, when you want to use this type on the right side, you can use the name instead. For example, my triples is a name for a list of 3 elements: number, boolean, and string. And int predicate is an alias for a function from int to bool. And actually, standard library Haskell base already has a few aliases. So for example, string is an alias for char. So that's why you can use char instead of, that's why you can use string instead of list of characters, because it's just an alias. Another popular alias is a file path. File path is just another name for string. And you may use this feature like when you have lots of really common, really similar elements. And you may write a function that does something. So here it takes 3 like different values and it calculates some result based on these values. And it may look fine because the type signature became more readable. So it looks more readable than like int. What does it mean? But the problem is that the type is not a new type. It's just another name. You still can pass different arguments and compiler won't be able to tell you if there is a problem. To solve this problem, you can use a feature called newtype. So newtype is for creating new types, obviously, as the name suggests. And you can define a data type as a new type if it has exactly one constructor with exactly one field. So instead of define our 3 types as type aliases, we can define them as new type. So new type is like data. You can think of it as a special case of data. It has a name and it has a constructor, but the constructor must have at least one field. And if you define a data type like this, you will need, again, to pattern match on the constructor if you want to extract fields. This is a new type with the constructor. And if you want to create new type, you need to pattern match on this. You may think, why go through all this trouble? Like, is it really worth it? So the benefits of using new types, well, its benefits of using new types instead of types is because it's a new type. It's like completely new type. And the compiler will check for you if you pass the unexpected type. So not just numbers, but they allow you to add some semantical difference. For example, title, description, name, these are all strings, but you might not always want to pass description instead of name. This is just another guarantees. But you would think, okay, it's a new type, like a completely new type. Does it have any overhead performance? And actually, no, new type doesn't have any performance overhead. So it's guaranteed by the compiler that all these wrappers that you have, unwrappers, they will be eliminated, erased, and your functions will behave exactly as you wrote it with ints, but they won't have this kind of like overhead of runtime. But the problem, the cost is to you need to use these constructors and need to wrap and unwrap. Just to write more code. So there are trade-offs. Okay, so we have lots of such types, like, but we don't want to define just types. We also want to write functions. How we can do this? Because we now have lots of types and we probably need to write lots of functions. Is there a way to write functions that work with like data type, with all the data types? And the answer is yes. We can write polymorphic functions. And the common polymorphism, which is called this parametric polymorphism, allows you to write functions that work for any type. So specific types in Haskell by Haskell naming conventions start with a capital letter, with an uppercase letter. And there are type variables, which tells that the type can be anything. They start with a lower letter. And let's write the first polymorphic function, this function called dup, it takes an element and returns a pair of the same element twice. So you see its type, it's variable a, not specific type, just some variable type, and we get a pair of the same type twice. And if we get a pair of chars, we get the same char twice. If we get a pair of booleans, we get the same boolean twice. And if we check the type of this function applied to specific value, we can see that the type is also corresponding. So this is a parametric polymorphism, a way to write functions that work with any type. You just use type variables, and they need to match. And actually, all functions that we've seen so far and we work, they're polymorphic. They don't work with just list of numbers. They work with all list of characters. They work with any list. So function like FST, it takes a pair of two elements, potentially of different type, and returns a. And you actually can see from the type here that it will return the first element of the boolean, because the pair has a and b, and the function returns a, and it's the first element. And the plus plus operator takes two lists of the same type and returns a new list also of the same type. So list must be of the same type, and so you cannot append like a string to a list of numbers. And higher order functions are also polymorphic, for example, and it's pretty clear that what's happening from that type signatures. For example, the map function, it takes a list of a's and it takes a function from a to b and returns you a list of b's. So you can think, okay, just probably applies this function to every element of the list and returns this. It's pretty clear. So you can think of this polymorphic functions as a way to write functions that work with any type at the same type. And one nice feature, like one really great tooling and in development tooling in the Haskell ecosystem is Hoogle, is not Google. It's a search engine for Haskell functions. It allows you to search functions by name or by module or by types. But most importantly, it allows you to search like polymorphic functions by type. You can just write a type of a function, what you want, and it will find you a possible function that matches this type. So let's see how we can use it. Let's say we want to have a function that takes an element and returns a singleton list containing only this element once. So how you can start to search for this function? You don't know its name, so you want to know how it works. So you might think, okay, you start to thinking about this function from the type. You think, what its type? Okay, the type of this function, it takes any value, so probably any value, so just some a, and returns a list. I want the list to have the same type as the value, so it will be the list of a's. So basically, I want the function from a to the list of a's. And if you write this type signature in Hoogle, if the first two results will be two functions. The first function is repeat. We can check the documentation. It says that it creates an infinite list with like the same element. So not a singleton list, not what we want. It's the opposite of singleton list. But the second function is called singleton, and it actually creates a list of containing only one element. And you can check documentation examples to see how it works. So it's pretty cool if you just think of a shape of what you want as a function, and Hoogle will try its best to find the function that matches you. And this is really neat. So we can have like polymorphic functions that work with polymorphic types, but can we have the polymorphic types themselves? And yes, so let's think. We have like chest, like in a game's chest with reward, and chest contains some gold coins, and it potentially contains some arbitrary reward, but it can be anything. So inside the chest, there can be any treasure. But we don't want to create a new data type each time we have a new treasure inside. We want to have something similar, and it's possible. You can have polymorphic data types in Haskell. You just write type variables after the name of the type, and you put these type variables after the field. So this is a chest. It has a gold, like integer number, and any treasure. And again, if you check the type of constructor, it's a function. It takes number, a value of any type A, and returns a chest of A's, some value, some type A. And we can have a chest of booleans. Well, booleans are pretty valuable treasure, so why not? And what's cool, we can have type aliases for specializing this variable. So like bronze chest, the simplest one, it contains only armor, and the golden one contains 3 fields. You probably in real life, if you would write system like this, like program like this, you want to have custom records, custom data types, and not tuples, but it's possible. You can then put them in some type, and you can write a function that takes some dragon and calculates maybe depending on how strong the dragon is, the reward chest, and it's still just one type chest. You can use it many times. And Haskell has lots of already common types which are polymorphic. So one of them is maybe. It's an optional value. It's a polymorphic type. So if you either have nothing or you have just a value. So optional value. Another popular polymorphic type is either. It's parameterized by two type variables A and B, and the first constructor has values of type A, and the second constructor has values of type B. So you see the different types, and you can specialize these types to have different values. So you can think of either like a maybe with a tag. So the constructors are generic, left and right, no special meaning. Usually left means error. So and the naming is unfortunate, but yeah, you can use not as an error. And actually lists are also defined as a data type in Haskell. The definition is very scary, so it uses a lot of operators, a lot of built-in syntax, and you cannot define your data types like this in Haskell. So this syntax is reserved only for lists like square brackets and colons. But if you wrote a list on your own, a polymorphic list containing values, you would write something like this. So just list of A's, it's either an empty list or an element A prepended to the list of A's. And this is basically the same data types, but in Haskell, just built-in syntax, maybe to for things to look more neat, more nice, more conscious. And you can write functions that work with such data types. For example, you can have an optional int, and you want to extract int from optional int, but like we cannot because there might not be int, maybe int. So let's just use some default value. If it's nothing, if there is no number, we return 0. Otherwise, we return our number, and if it's inside just. You can write functions that return these polymorphic types. For example, this function find, it's a higher order function. It takes a predicate from an element to the Boolean, and it finds the first element that matches the predicate. But it returns maybe because there might not be such element in the list, so we don't know if there is any element matching our predicate. So in the first example, we want to find the number the first number that is bigger than 4, and there is no such element in the list, and we return nothing. In the second example, we want to find the number bigger 4, and there is just 5. So the first number is just 5. Or for example, you might want to have a list of different two types. So lists in Haskell might need to have only the same type, but if you want to have different types, you can put them inside for something like either. So here we have a list of either numbers or strings, and we can use function like partition eithers to get the list of numbers and the list of strings. So this is how you can work with polymorphic data types, and this is a really nice way to model your programs, your types, and yeah, please practice. Oh, we talked a lot about data types, but let's now return back to functions. So in the end, we still want to write functions that work with different data types. So a nice feature about functions that I haven't told before is called Eta-reduction. And Eta-reduction means that if we have two functions, f and g, and if for any value x, these two functions are like the same, we run them on x and they return the same result, we can say that these two functions are actually equal. And what it means is that in the code, we can write them as equal functions. So let's write a function showInt, which converts a number to the string. And we say that showInt is just show n. But I mean, we can Eta-reduce this function. Eta-reduction means that we can remove like the common suffix of the function on the right hand side of the equal sign and on the left hand side. So just showInt basically is a show. We don't need to write this element, this argument n, and we can make our code a little bit cleaner. Let's look at more examples. Again, remember that you can partially apply functions and they still will be functions. So we have a function only even that applies filters only even elements. We can remove the common suffix of our function and Eta-reduce because filter even is already a function, and basically our only even function is equals to the filter even. We can simplify this code. Let's look at another example. there is nice higher order function called zipWith. It takes a function from A, B to C. It takes a list of A's, a list of B's, and a list of C's. And what it does, it applies the given function to two lists pairwise. And again, we can use this function to write to find the product of two lists by elements. And we write this like a function prod that takes two lists and just applies zipWith operator multiplication to these two lists. And we can actually also add to reduce this function, and we can even add to reduce two arguments. So how it works, you see, okay, if there is common suffix like ys and ys on the side, we remove it. Okay, we see, okay, now there is common suffix xs and xs. Again, we can remove it. So partially applied functions also return functions, and we can use like something like function equality. So this is a nice feature, and you can do this Eta-reduction, but it doesn't mean you always should. So most of the times names don't really matter. So what is this, like x's, y's, what does this mean? We can just remove them. I don't get any new information from these names. I've seen so many x's, I don't even care anymore. But sometimes names like are really useful if you like write a function that extracts some users from a database, some entities, and it might be really helpful to have a name of this variable, even if you like can add to reduce it. So you don't always need, and it's considered like use your judgment when the name is really helpful. This is cool. Okay, why do we need it? This feature of Eta-reduction actually plays nice with the so-called function composition. So let's first talk about composition of functions. This is the last topic of the lecture, the final one. So the composition of functions, remember, it's in functional programming, it's really important to be able to compose two functions. And function composition in Haskell is just an operator, which is dot, just dot, which takes two functions and returns a new function. So if you just look at this definition, it can explode your brain. Like, what's really happening here? What is this? Like dot and round brackets? What is this? F, G, A, B, C? It maybe doesn't make sense. So let's first look at an example. It's like a very simple example how we can understand function composition. So let's say we have a defrost function, which takes a frozen broccoli and returns just plain broccoli, non-frozen, just warm. And we have a function cook. It takes just a raw, fresh broccoli, and it cooks them, and we get a pan. Don't ask me why there is a pan of prawns and not of broccolis, but it doesn't matter. So what we want to have a function that takes frozen broccoli and returns like cooked broccoli. We want to have a function cook. So you can see from the types that it's actually like a two-step process. We just run defrost to get broccoli, and we just run cook to get our meal. It's pretty nice. And we can define our function using function composition. So we use this dot operator, this dot between two functions, and you read it from right to left. So the first function written is cook, and the second is defrost, but actually it's the first function that actually will be run, that will be the first action that will be performed is defrost. So we defrost our broccoli and we then cook them. It's pretty neat. So another way to look at this is by using like this diagram with arrow. So in category theory, such diagrams are called commutative diagrams. We just call them like paths and arrows, how we can cook broccoli. We don't really care about theory behind these diagrams, but what it means, you can think of functions as paths between types. So we can go from frozen broccoli to fresh broccoli, like this is a defrost function, this is like arrow, and we can then cook our fresh broccoli and get a meal. So if we can do this in like step, we can like have another function that moves us from one state, like frozen broccoli, what we have now, to the desired state. Like when we want to have a meal, we want to eat. It's pretty late in the evening in the end. So we just use this composition, and the composition allows us to create a new function. So let's return back to this operator. What does it mean? So this is an operator. Again, a function composition is just a function. As I said, everything in functional programming is function. This operator, it takes two functions. It's a higher order function. It takes two functions, function from B to C and function from A to B. And it returns us a function from A to C. And you may think that, okay, it actually takes three arguments. I can see it takes two functions and the value of A. But again, remember, you can partially apply functions and you can return functions easily. So if we just specify the first two arguments, we can return a function from A to C. It's like this. And what we do, we have A, we have a function from A to B, we have a function from B to C, and we want to have C. So again, this is like pretty straightforward problem. You just apply function from A to B, you get B. You apply function from B to C, you get C, and voila, you get C from an A. This is just an operator. And it's like written this way because you usually don't specify it like to three arguments. So usually when you write operators, it has two arguments on the left side and on the right side. And when you just use a composition of functions to apply it to a single element, it doesn't look nice. So like you see, this is length and composed with a show to apply to true. So what is going to happen? We are going to run show first. So we are going to convert this true to a string of 4 characters, and then we are going to calculate length of the string, and it will be 4. So it doesn't have lots of benefits for us now, but it's nice when you want to pass a higher order some function to another higher order function. For example, we have a list of strings, list of sentences, and we want to calculate how many words in each sentence. So we just apply a composition of function words and less. We just split each string to words, and we apply length to get the number of words. And you can compose more functions. It's pretty neat. So I promised that Eta-reduction and composition play nice together. And let's see how these two features can help us to simplify some of the existing functions. So we want to write a function that takes a list of lists and returns the first 5 lists of even lengths. That's all. So its type signature is a list of A's. Again, we don't care what's inside the list. It's a polymorphic function. It works with any lists, and it returns the list of the same type. So what do? We apply first function filter to our list. And we have a list of lists. How we filter? We calculate the length of the list, and we then check if the length is even. So this will allow us to have only lists of the even lengths. And then we take the first 5 elements. So that's pretty straightforward. Let's rewrite our lambda using function composition. So again, this is just a composition of functions even and length applied to the L. This is just a straightforward syntactic construction. And you can see, like, wait a minute. So this lambda is basically just function, just this function. We can add to reduce this L argument. We don't need to have this lambda. We can just pass the composition of even and length to the filter. We don't need to have this lambda of this round brackets. That's nice. Okay, the next step is to do the same with the take 5 and filter function. Let's apply the composition of filter and take 5 to the list, and we'll see, okay, I can add to reduce this function again. So basically my take even 5 is the same as the composition of these two functions. And this is a final form of our functions. And I say that we are going to simplify this function. And if you are not so comfortable with the function composition, this might not look simpler. You might say that, like, the first version is already was simpler enough. Why do you need to go through this trouble? But actually, when you become more comfortable with this notation, when you see it, you understand that actually these variables, and they might be some noise. You can, if you think of a program like more high level, what you do, you basically just convert all the data from one form to another. Your program is just a huge pipeline of transformation. And what you do is just compose function. You get one element, you give it to first worker, they do something with your values, they pass it to second worker, and so on. So basically your data just moves through different pipelines of transformations. And this is just function composition. You just compose different functions. And ideally your function, like your main program, just composition of some functions over your data transformation. And I encourage you to practice this function composition. You can go to the exercises in the first lecture and maybe rewrite some functions using this composition. There is particularly one line function that's pretty neat, can be rewritten using function composition. And that's all for today. thank you for listening to me. Sorry, there is a bit of delay. Probably was a bit nervous. And here, these are the more resources which you can read to learn something new if this lecture was enough, or maybe if you want to dive more into these topics. I want especially to highlight this Cube Composer. It's a game. It's written in another functional programming language called PureScript. You can play it in your browser. And it helps like to understand function composition nicely by composing some standard functions and to have cubes. It's a nice game. And there are other resources. So again, thank you very much for coming to my second lecture. And this is all for today. And if you have any questions, please write them in the chat. I will try to answer as many as I can. Ooh. I see the chat was pretty active during the lecture. Our first homework was quite intensive. I literally spent an hour to figure out how to print formatted string. Well, wait for the second exercise, for the second homework. It's going to be even more intensive. And yeah, there's one thing you can ask in the chat. There's a Telegram chat. Feel free to ask any questions. I might be able to answer, or if not, maybe someone else is online and can answer them. Speaking about arithmetic operators, what about slash equal sign? So slash equal sign is not an arithmetic operator, is an operator for comparing values. So just not equal operator for not equality. Yeah, I see it was answered. Yeah, it looks like division in other languages, but like operators like plus, equal, minus, equal, they mutate variables, so kind of like change variables and assign, but in Haskell you cannot change. And yeah, this not equal sign looks like in math in school when you put the equal sign under the slash. But if you use some font with ligatures, you will be able to see this like kind of neat written way of not equal sign. How to create a user? Yeah, there is a constructor. As I mentioned, the constructor is a function to create users. Why are we using type constructor while deconstructing value? We're not using type constructor. Well, constructor can be used in both ways. It can be used either to like construct values or to deconstruct values, like in pattern matching. So constructors kind of like plays both ways. Is there any difference between such polymorphism and generics in other languages? So depends on the language. So generics can be different. There is like theory or what types of polymorphism there are. And not tomorrow, next week, we are going to talk about different type of polymorphism. So today I was mentioning parametric polymorphism, and we are going to talk about ad hoc polymorphism. So these are different types of polymorphism. And actually, there are lots of types of polymorphism. So there is like a structural polymorphism. This is like third type. There is also like Levitsky polymorphism and many others. So there are many ways you can write polymorphic functions, and depending on over what you're polymorphing, over which part. Does Haskell have generics? Yes, it does, but it's probably not the generics you're thinking about. Hoogle is awesome. Yes, I agree. It's pretty awesome. And lots of people think that Haskell tooling is amazing just because of Hoogle. You can just type a function. And I encourage you to do this during second exercise. If you, instead of trying to write your own functions, so you kind of practice writing your own functions in the first exercise, but try to think what function would be nice to have. And there is a good chance that a standard library already has it, like good, like not 100%, but a good chance it might have it, especially if you think about the proper type. Sorry. Is dot like pipe operator? Well, we can think of it like pipeline. There is another operator, dollar. I won't go into cover this during course, but you can check its types, really popular. If you understand function position, you can understand dollar as well. There are also some examples or maybe some blog posts. Yeah, already scared of the second homework because the lecture was pretty hard. According to my experience, this algebraic data types and the type system in Haskell is the most difficult part. So the second homework might probably be the most difficult. So far, the rest will be easy. So monads, they're not a problem at all. But this, like, understand this algebraic data types, these concepts can be really mind-blowing. And I'm sorry if you will spend lots of times, but feel free to ask any questions. Let's try to help each other. Is there a way to force completeness, exhaustiveness checks in the following scenario? And there's a function from string to color. So what do you mean force exhaustiveness? You wrote a function that pattern matches on a string and returns the values of type color, but strings can be different. Not only these three constructors, not only these three values. You can put the final pattern underscore, but again, the problem is that if you add new constructors to the color, you will get an update that you need to like change the function that takes a color and returns string, but you won't get an update on the function that takes a string and returns color. And there are different ways to do this. So I wrote an alternative standard library to base, and it has a function, a helper function that does this. So you write only one function from color to string, and this helper function automatically gets you the function from string to your color. So you don't need to worry about that. This is a one way how people do, and there are multiple ways to write this function. So polymorphism is polymorphic. Yes, it's a meta polymorphism. Will we ever have something like Rust mem management to produce more performant code? I want Haskell to be more famous than Rust. Well, this is a point of like kind of high level language that you actually don't always want to manage memory. So most of people don't realize it, but they don't want to manage memory manually. They need to do this sometimes because the performance characteristic might be kind of tight, but they don't want to do this. And Haskell handles this for you because it has garbage collector, so you don't need to worry about this. But there are, of course, ways to write more low-level code in Haskell to kind of control, maybe to decrease memory consumption, your memory footprint. So there are ways, but I would say they're more advanced and don't really want this. What are the advantages of the dot operator? Yeah, the code looks clear, so less round parentheses, less round brackets, less variable names, especially useless variable names. And on a more high level way, it's just a composition of some functions. So you just have steps and you basically just run your input through the composition of this function. Just a way to define how to combine multiple functions. So you can write lambdas, of course, but when you have lots of functions, it becomes really tedious. Okay, I don't see more questions in the YouTube chat. Again, thanks for coming to this lecture. I remember I wrote that you still can write exercises to submit solutions to the first lecture through this week or the next week before the course ends. So yeah, see you next week, and feel free to ask any questions in the chat.